So we've got to kind of get back into this topic of trigonometric integrals and to kind of pick up where we left off yesterday at the end of class. We had covered, first of all, how to develop a technique for when there is an odd power of cosine or an odd power of sine in your integral. You peel off one of those powers, make a substitution with the Pythagorean identity, and that gets you home. So Pythagorean identity plus a u substitution works when there's an odd power of cosine or an odd power of sine. But where we left off yesterday is thinking about an integral that has only even powers of both sine and cosine. And the first move was that we wanted to translate everything into either all cosines or all sines, which we can do using just the Pythagorean identity. In this example, trade out sine squared for 1 minus cosine squared. So once everything is in terms of cosine, now just distributing, we find out that what we're up against is we really have to do an integral of the fourth power of cosine, an integral of the sixth power of cosine, and the handicap here is that we don't know what the antiderivatives of the fourth and the sixth powers of cosine are, but we do know the antiderivative of the second power, right? Cosine squared. We used a trig identity last time to come up with the antiderivative for cosine squared. So it's there down at the bottom. And so if we somehow can get our integral to be reduced from a fourth power of cosine down to a second power of cosine, then we would know how to finish. Because the purple formula down there at the bottom would tell us the antiderivative of the second power of cosine. So let's see if there's a way. So what we're going to do is we're going to set up an integration by parts, but it's actually not the integration by parts that we were thinking of last time. Instead, we're going to try the trick of peeling off a single power of cosine, just like we used to do with the odd powers, except that after we peel off a power of cosine, we aren't really set up to use a Pythagorean identity here, because we don't have a cosine squared in here anymore to substitute 1 minus sine squared for. We're going to integrate this by parts. And because we don't, in general, know how to integrate odd powers of cosine, or we do, but it's complicated, right? We would have to, if we wanted to anti-differentiate cosine cubed, it would be kind of a mess. So we're going to pick, instead, to differentiate the cosine cubed portion, and to anti-differentiate the cosine, the single power that we peeled off. So in our integration by parts, the role of u is going to be played by cosine cubed of x, and its derivative, according to the chain rule, is negative 3 times cosine squared times sine. And then v prime, cosine x, its antiderivative is just sine x. So that antiderivative is not so bad. And now doing the integration by parts, we need the product of cosine cubed times sine. So we need that diagonal in our table, minus the integral of this horizontal, minus the integral of u prime times v. So all in all, we end up with cosine cubed x times sine of x minus the integral of negative 3 cosine squared x sine x times sine x. Negative 3 and the minus in front of the integral sign make a positive 3, which we can pull out in the front, and the two powers of sine of x combine together to give me a sine squared. So at first glance, it doesn't really look like we've made much progress. We've traded out a cosine to the fourth integral for cosine squared times sine squared, which is also kind of a degree 4 expression in the trigonometric functions. So it doesn't look like we've made progress. So to reclaim our progress, we have to do our original step again. The step that we did in the very beginning, which is let's trade out our sines and turn this into all cosines. Or I suppose we could have traded out the cosines and made this in terms of all sines, but you'll see why this choice is better in just a second. So how can I use the Pythagorean identity here to get me back into all cosines?
You could take out cosine squared of x.
This one?
Yeah, and turn it into, what is it, 1 plus sine of x squared? No.
Well, if we took out cosine squared, it would become 1 minus sine squared.
That's what I meant.
After we did that, our integral would have only sines in it. It would have a sine squared in it, it would have a sine to the fourth in it.
No, you still have an extra cosine.
We would have a cosine, but it wouldn't be in our integral. It would be out in the front here. So actually, I want to do something like this, but I want to do it with not the cosine term. I want to trade out the sine term instead. In other words, I want to re-express my integral in terms of using just cosines instead of just sines, right? We could do it either way, but if I can re-express this using just cosines, then I might be able to relate this integral to the original integral that we started with. So what I mean by that is, let's trade out sine squared for 1 minus cosine squared instead. And after we've done that, now we end up with, inside our integral, after distributing cosine squared across 1 minus cosine squared, we end up with the integral now of cosine squared of x minus cosine to the fourth of x with respect to x. And again, it doesn't look like we've made progress, because our integral still has cosine to the fourth in it. So what comes to our rescue here? What do we have to do in order to make any progress on this integral by parts, now that we have come back to where we started? Well, that's where we're going, right? And in fact, what I'm doing here is showing where the reduction formula comes from for this.
Substitution.
Well, substitution, except that if we tried substituting for a cosine, we don't have a sine to absorb our du for our substitution. So this is a technique we've alluded to before, but haven't really followed through on yet. And that is, notice that our original integral, the integral of cosine to the fourth, is also a part of the reduced integral that we've gotten now by parts. So if we call that original integral I, which is what we're interested in finding, then I satisfies I is equal to cosine cubed x times sine cubed x plus 3 times the antiderivative of cosine squared x minus 3 times I. We're going to see where that is coming from here.
Well, you wrote fast.
Yeah.
I'm a little lost.
Okay. And now we just need to solve this equation for I to figure out what the integral is. So to solve this for I, all I have to do is move the 3i, the negative 3i from the right-hand side over to the left-hand side by adding it. So that now on the left-hand side I have 4i, remember I is the integral we're trying to find, is equal to cosine cubed of x times sine of x, plus 3 times the antiderivative of cosine squared of x dx. And so to finish this thought, to solve for our integral of cosine to the fourth of x, all we have to do is divide by 4. So divide that all by 4, and there's the value of this integral. 1/4 times cosine cubed of x sine x, plus 3/4 times the antiderivative of cosine squared of x dx.
What is that again? Identity?
So I is the value of this antiderivative that we were interested in finding in the first place. I is our goal here. The antiderivative of cosine to the fourth. And notice that we haven't really finished the work yet, but we have expressed I, the integral we're interested in. We haven't finished the calculus really, but we have figured out how the antiderivative of cosine to the fourth can be expressed in terms of the antiderivative of cosine to the second. And that's an example of what we call a reduction formula, because we've reduced the number of powers of cosine from 4 to 2. So the reduction formulas are all derived in exactly the same way that we just derived a reduction formula for cosine to the fourth. And that is just using integration by parts, integrating by parts in a circle, and then solving for that value of I. And if you look in the text, the reduction formulas look something like this. So the reduction formula for even powers of cosine looks like this. Yeah, if you haven't looked at the Rogowski section, you'll understand why this is one of my less favorite things to talk about, just because it looks intimidating. But again, what's the moral of this story? The moral of the story is on the left-hand side, we have the integral of some large power of cosine. Meanwhile, on the right-hand side, we have another integral, except the number of powers of cosine is 2 fewer on the right-hand side than it was on the left-hand side. So where we started in our last example, which we're going to finish in a second here, where we started with an integral of cosine to the fourth of x, the reduction formula shows us how to turn it into something which, instead of cosine to the fourth, has cosine to the second in it.
You know what else it proves? Mathematicians and masochists. What's that?
A little from column A and a little from column B. But just because it looks intimidating doesn't mean that it's necessarily not useful.
That's just for even ones.
And this is, well, honestly, it works for all powers. But it's only really, we only find it necessary to use it for the even powers. Because for the odd powers, the technique we talked about yesterday, peel off a power and then use a substitution, that will bail you out. For even powers, this is really the only way forward.
So instead of doing that long way, we can just simplify it.
We can just use, right, exactly, we can just apply a reduction formula. This is also not a formula I'm going to ask you to memorize. I'm talking about this with Daniel. So that if I expect you to use a reduction formula on a quiz or a test or something like that, I'll provide it for you in a little crib sheet off to the side. So I'm interested in, first of all, that you have an understanding of where these formulas came from, and then second, how to use them, which is what we're getting to right now. In addition to this formula for the powers of cosine, there's also an analogous formula for the powers of sine, and it's analogous because it looks almost identical. All we have to do is, first of all, change the cosine in the integral to a sine. And then on the right-hand side, we first have to flip the sign on the very first coefficient. Instead of minus 1 over n, it's now plus 1 over n. And then go through and change all the rest of the cosines to sines and all the rest of the sines to cosines. And there we have a reduction formula for powers of sine instead. Again, they're all coming from exactly the same place, just the integration by parts formula. So, what do we know? What does this allow us to do? Well, it allows us to take cosine squared of x, which is a function we might be interested in finding an antiderivative for. And we already knew what this antiderivative was, based on a trig identity yesterday. It was x over 2 plus 1/4 times sine of 2x. Plus c, really, but I'm going to leave the plus c out of this little table, just to keep the focus where the focus belongs. So this was found yesterday using a trig substitution, or using just a substitution method, and an identity. So we didn't have to do any super fancy, reduction formulas to find that. So that's kind of our base case, if you like.
You can't really use that formula for that.
Exactly. You can't really use this formula for cosine squared. Yeah, that's, I think, a true... Well, is that true? Actually, I think you can. Secretly, you can use this formula for cosine squared, if you like. Try it sometime. It only takes one step, actually, because then you would end up with cosine to the 0 inside of this integral, which is just 1.
Yeah.
And the antiderivative of 1 gives us our x that we end up with over here. So, and sine of 2x is, according to the double angle identity for sine, equal to 2 times sine x times cosine x. And that's going to account for the first term. So secretly, the reduction formula also works for cosine squared, even though we probably wouldn't use it for cosine squared because there's a simpler way. But what the reduction formula does is, again, tells us how the next integral up, cosine to the fourth, relates to our first integral. So according to our work that we did, according to the reduction formula, cosine to the fourth of x is equal to this thing, 1/4 times cosine cubed times sine, plus 3/4 times the antiderivative of cosine squared. But what's the antiderivative of cosine squared? It's exactly that thing that's in the first row of our table. So we need the first row in order to determine, finally, the antiderivative on the second row. And I'll just replace that integral of cosine squared with the thing that's on the row above, x over 2 plus 1/4 times the sine of 2x.
What was that before, the integral?
It was the integral of cosine squared of x. So rewinding that just a second, it was, and this was coming from our reduction formula. That was this term. And again, it only helps us because we already knew what the antiderivative of cosine squared was. It was on the line above. And then simplifying this, letting all the dust settle, multiplying that 3/4 into what we have here, we end up with 3/8x plus 3/16 times the sine of 2x. And there is our antiderivative for cosine to the fourth. But now that we know the antiderivative for cosine to the fourth, we can find the antiderivative for cosine to the sixth using the reduction formula. So now n is equal to 6 in our formula, and so we end up with, oops, I think I'm missing a minus sign in maybe a couple of places. I think I'm missing one there, and I think I'm missing one there. Again, from the reduction formula that we have the minus sign in. But then it starts with negative 1/6 times cosine to the fifth of x times sine of x, plus 5/6 times the antiderivative of the fourth power of cosine. But what's the antiderivative of the fourth power of cosine? It's that stuff that's on the second line. And so we would then have to substitute that whole big expression in for that integral and simplify what we did. And then we have an antiderivative for cosine to the sixth. But what you notice is that things get sort of exponentially more complicated the higher up that we go here. So let's fix this for the record. That minus sign actually belongs with the sine formula and not with the cosine formula. So my apologies.
Okay, Okay, so the reduction formula.
So in your reduction formulas, head back into your reduction formulas on the left here, erase the minus, which was in the cosine, erase the plus, which was in the sine, and the minus belongs down here, plus belongs up there. Sorry about that.
The other two are just.
Right, so over on the right-hand side here, we didn't need the minuses in this table. So here was the antiderivative for cosine squared. Right? That's the one we started with. That was the first row of the table, x over 2 plus 1/4 times the sine of 2x. What comes after that? Oh, absolutely. Well, I want to make sure that it looks like you would expect to see it in a textbook. Otherwise, it looks kind of like code, and I don't want it to look like code. So then what would be, let me also make sure we can see what the exponent is. Whoops, missing a brace there. Okay, hide the code. So here's the antiderivative for cosine squared. Antiderivative for cosine to the fourth, we said was, oops, here we go. So for cosine to the fourth, here was the antiderivative we had before. And actually they're written in a slightly different way here. They had taken the cosine cubed of x times sine of x and changed it into a sine of 4x. So this is just Mathematica's take on it. It's completely equivalent to the antiderivative we had before, just a little bit written in a different way. Here's cosine to the sixth. It ends up having all these terms in it. Sine of 2x, sine of 4x, sine of 6x. Cosine to the eighth. Cosine to the 10th. Cosine to the 12th. Yeah, how about cosine to the 24th?
Let's do it.
Sure, why not? I gotta scroll this up here. See, this is one of those tasks that computers are just ideally suited to do. Here's cosine to the 24th. So one of the reasons the reduction formula is not all that practical to use in a general situation is that it is recursive, right? That the fourth power depends on the second power. The sixth power depends on the fourth, which depends on the second. The 24th power, the reduction formula would turn into an integral of the 22nd power, which the reduction formula would turn into an integral of the 20th power, which the reduction formula would turn into the integral of the 18th power, and so on and so on and so on, until we got all the way down to cosine squared again. And there, that antiderivative we knew. But by the time all of that dust settles, we end up with all kinds of stuff going on in our antiderivatives. So this is, I guess, why I don't like the reduction formulas that much, is that they're just not practical in a general situation. They can tell us how to reduce kind of small powers of cosine and sine, like maybe cosine to the fourth, maybe sine to the fourth, maybe cosine to the sixth if you're feeling like you particularly have a lot of time on your hands. But really, anything more than that, it just, you end up down this rabbit hole of having to do calculation after calculation after calculation. And so I guess the moral of the story is most of the time, you're not going to be using reduction formulas a lot, just for small powers of sine and cosine.